Welcome to the seminar on the science and exploration of Phobos and Deimos. I'm Dan Britt, and I will be moderating today. And we have today Dan Scheeres, who will be talking about microgravity and structure in the Phobos and Deimos system. Dan came to planetary science by a circuitous route, like many of us. He started out did his PhD in aerospace engineering at the University of Michigan. Spent about 5 years at JPL doing celestial mechanics and navigation, and has been an academic nomad going between Iowa State, University of Michigan, and finally settling at the University of Colorado. And at Colorado, he heads the Celestial and Spaceflight Mechanics Laboratory. And his interest primarily these days is in how the properties and geophysics of asteroids affect things, affect exploration, and how asteroids can hold themselves together, in particular when they're essentially piles of rubble floating in space. And so he's done a lot of amazing work looking at the interparticle forces that hold small asteroids together. He's also the science lead for the OSIRIS-REx asteroid, or radio science lead for the OSIRIS-REx sample return mission. And I work with him on diverse things, including the Center for Lunar and Asteroid Surface Science and the asteroid retrieval mission. So I'm looking forward very much to hear what Dan has to say about the Phobos and Deimos system. Take it away, Dan.
Okay. Thanks for that introduction, Dan, and I'm very happy and honored to be here virtually, if nothing else. And I'll be
break in just a second real quick before you start and just point out I forgot one thing, which is as moderator, I will be handling the questions, and I urge the entire audience to participate by using the chat box to ask questions and make comments as the speaker gives his presentation. And primarily at the end, we will be concatenating those, and I will be asking the speaker questions. And part of the interest that I have in this series is the good questions and discussion that we've been able to develop out of the chat box remotely from the audience. Sorry for for breaking in, Dan, but you're on again.
Okay, no problem. So my screen should be showing. If it's not, please someone give me a text or something like that and let me know. And although I originally, when you asked me to do this some months ago, I think the initial thought was we would, or I would present something on sort of microgravity forces and the regolith and all that in the Phobos-Deimos system. It was sort of interesting to me because I haven't really looked closely at the system for many years, and maybe a decade or more ago when I was at JPL, I'd done some work on the system. So I was excited about it. Although when I started looking at it, first of all, I realized that it's not a microgravity situation. It's actually, as you see in my slide, a milligravity situation. It's still interesting, of course. But also in looking at the content of the presentations, I thought it would be very relevant to focus a bit also on the sort of the dynamics of motion inside of these interesting and somewhat strange regimes. So I do talk a little bit about sort of the relevant forces acting on particles and that environment in this talk, but I also talk a bit about sort of the dynamics in the system, and I think that's probably equally of interest to a lot of the people dropping in for these lectures. So with that as an intro, let me keep on going. So it's sort of a very brief outline. My goal is to really describe the dynamical environment about Phobos and Deimos. And to do this, we have to talk about the gravity, the tides, the rotation of the system. And essentially, we'll define something called the geopotential, which is related to dynamical motion, but it's related to a lot of other things too. We'll talk about that. I will talk about the importance of other forces and how they can be compared in this particular environment. And I'll come up with some interesting constraints that exist for motion on and in the Phobos-Deimos system. I know that part of this talk or part of these series are motivated by an interest in exploration. And some elements of exploration actually put elements, landed elements on the surfaces of these bodies. And when you start looking at that and how you might want to move around, there's some really interesting things that you have to take into account. So I'll touch on that too. It should be actually kind of fun. And then I'll talk a little bit about the orbital environment too, because for any exploration, you also need to get a satellite there, a spacecraft there, and you need to understand what you can and can't do. And there are some really strong constraints on that. So that's sort of an outline. Just a shameless plug. A lot of the methods and methodologies that I'm using are actually sort of codified in a book I wrote a couple years ago. So if you're interested in digging deeper into this, I can point you to where you could get this. And since this is a graduate class, I thought it was relevant to have a few equations here and there. So we'll actually start off just talking about how do we come up with a model for motion about Phobos and Deimos. And the easiest way I thought was to actually just sort of sketch out some notes. So here we have a picture, a cartoon of Phobos, say, with its long axis pointed toward Mars, which is over on the right. I got a couple of bits of information. The Phobos orbit period and spin period is like 7.6 hours. It's got a certain density. And this little black dot up here, this is what we're interested in. What's the motion of this dot? And this guy's acted on by essentially three main forces. First is or accelerations, if you will. The attraction of Phobos itself, G sub P, the attraction of Mars, G sub M, and since we're locating this particle relative to Mars, or I'm sorry, relative to Phobos, we also have to take into account the gravitational attraction of Mars on Phobos. So these three guys all combine together. We can write our equations of motion, the R double dot, or the acceleration acting on this guy in an inertial frame is equal to, way over on the right-hand side, these two attractions from Phobos, from Mars, and we have to subtract off the acceleration of Mars on Phobos to make it all work out right. And we want to jump into a rotating reference frame. So when we do that, we have the acceleration relative to this, rotating Phobos. We have the Coriolis acceleration, and we have our centripetal acceleration. And let's introduce a coordinate frame here. X, Y, Z. X is pointing at Mars. Y is going in the opposite direction. Maybe we should have chose X the other way, but this is the way I chose it. And Z is out of the plane. So really, Phobos is rotating around the Z-axis. If we use this, then we can actually rewrite the centripetal accelerations like this spin rate squared, omega squared, times the X component times the Y component. And we can also, it turns out, make some approximations for all these gravity terms that are mixed up here. And we still have the attraction of Phobos. We're not going to touch that for a moment. But we get this weird guy over here, twice omega squared X minus omega squared Y minus omega squared Z. And this is all in different vector directions. And, we can equate these two sides, rewrite this, and we have the equations of motion. Acceleration plus Coriolis acceleration equals the gravity attraction of Phobos plus this, what we call tidal term, 3 omega squared X. And means that the farther we go away from the center of Phobos in either direction, the stronger force we feel pulling us even further away. And this omega squared Z minus omega squared Z, which means as we go out of the plane, we actually feel a greater and greater attraction back to the plane. And this is what's called the sort of the tidal perturbation acting on any arbitrary body that's moving in this system, whether you're on the surface or you're in orbit. So let's just rewrite these, and I don't have that many equations, but this is just another slide of them. And this is, if we want to write it in this XYZ coordinate frame that I just defined, this is what it would look like. Pretty straightforward. This G here is really the gravitational attraction of Phobos, Dymos, and that's really just the gradient of this thing, which we call the force potential, and this is an integral over the mass distribution of Phobos or Dymos. And this is sort of a gnarly guy to compute, but there are many different ways of computing it. What I'm using for everything I show here is sort of a nice result. It's a very classical result, although it was really rediscovered by Bob Werner, man, maybe 20 years ago or so. And what this gives us is, for a constant density arbitrary shape, it tells us exactly what the gravity potential is and what the gravitational acceleration, if we take the gradient of that guy. And you can actually use it to solve Poisson's or Laplace's equation. Very nice result. If you really want to dig into modeling this environment, you sort of need that result. And it's like it's written up in my book. The paper is pretty easy to find as well. And if someone has a question, you can always come to me and ask. I get a lot of questions every year about that. So with this gravitational potential defined, we can actually rewrite the right-hand side of these equations using this function we call V, which is the geopotential. And that's minus 1/2 omega squared times the quantity, 3x squared minus z squared, minus this force potential. So this minus u is really the gravitational potential of a point around the Phobos or Dymos system, just accounting for the attraction of that body. The rest of this stuff sort of quantifies the effect of the fact that Phobos and Dymos are rotating and that they're in the strong gravity field of Mars. So with the geopotential, we can rewrite the equations of motion, and they come out to be a really simple form. Acceleration relative to that Phobos or Dymos plus Coriolis relative to it, and this is the velocity relative to Phobos or Dymos, and then the negative gradient of the geopotential. Okay, so that sort of defines the mathematical framework for it. So what does this geopotential look like? And here's a plot of it mapped onto the surface of Phobos. And there's a couple interesting things here. And actually, I didn't realize these until I was going through preparing this talk over the last couple weeks. It turns out that the highest points in the geopotential are actually along the Phobos leading edge, and especially its trailing edge. And actually, I'll have a couple comments about that later. For a system like this, you might expect it's relatively slowly rotating. You might actually expect that the highest point in the geopotential would actually be at the polar regions, and it is relatively high there. But the highest points are actually in the leading and trailing edges. This is just plotting that function on the surface. This is if we want to convert it into a height, although it's not quite that meaningful in terms of a height, but some people like to work with heights. And what I'm going to do now, and I'm going to do this through the talk, is sort of jump back and forth between my talk, and I've got some cool, or somewhat cool models of 3D models of these quantities mapped onto the surface of Phobos and Dymos. I'm mostly going to show Phobos for the surface stuff, although if people are interested, I can pop up the Dymos ones too. And we can actually go full screen, and then you can sort of look around and move this sucker around. So right now we're looking down onto the top. Mars is off to the right, and then this top one is what we would call the trailing edge, because this guy is moving downwards into the plane, if you will. And then this is the leading edge. And here you can explicitly see that the maximum values of the geopotential, the bright yellow, is actually along the trailing edge of the body and the leading edge of the body. And it's not at the poles. And in fact, if you go on the bottom, there's actually a, sort of a concave region, convex region. So that's naturally of lower potential anyway. The lowest point on the surface is actually pointing at Mars. And this is, if you wanted to measure the lowest point, you would start from here and also at the other end as well. And some of these things are sort of expected, but this Y high in the geopotential is a little bit interesting. Okay, so I'll be doing that a couple times, jumping back and forth to this guy or to these three-dimensional views when it's interesting to look at. So we can also look at the surface accelerations mapped over Phobos, and this is why it's a milligee environment, because they're all less, range from over 3 to less than 7, or 0.3 to 0.7 milligees on Phobos, and for Dymos it's a little bit less. It's a smaller body. They're less than 0.3 milligees across that body. Here you see that the maximum accelerations are in the polar regions, and the minimum accelerations are actually along the line pointing to Mars, where Mars is off to the right here. So what this really means is it's not a microgravity environment, it's a milligravity environment. And what does that mean? Well, even for this situation, it does require us to reconsider the importance of weight in these environments. Now, asteroids, especially certain classes of asteroids, the oblate, fast-spinning asteroids that you find typically as primaries of binary systems, those can have true microgravity or even less than microgravity environments that points on their surface. And that's something that's interesting. And one of the things that I'm going to be excited about trying to understand better for the OSIRIS-REx mission when we go to Bennu, because it has sort of an environment. But for Phobos and Dymos, the surface acceleration environment, even though the dynamical environment, but the surface acceleration environment is really more analogous to Eros, which was also sort of in this milligee, less than milligee range. Now, when you jump into these sorts of systems, there are a number of important effects to consider, and these all arise as a function of a particle's size. The first is the weight of a particle, which is mass times the ambient acceleration, and we all know that this goes as d cubed, as the volume of the body. Next is electrostatics and radiation pressure. This tends to go as the body squared. And the third is cohesion, which just goes as is really proportional to the radius or just the linear size of a body. Now, what happens in these low gravity environments is this ambient acceleration decreases, and as this decreases, the effects of the other non-gravitational force become more and more significant. In our research, we've really focused on cohesion and also a bit on electrostatics and radiation pressure as well. So you can actually compare these different forces, and this is a somewhat complicated plot from our 2010 paper. The important thing to note here is for Dymos and Phobos, the milligee line is here, and here we have particle radius in terms of meters, and the force that is exerted on this particle in a milligee environment. So a 1 millimeter size grain feels a weight of, this is like 10 to the minus 5, 6, 7, 8 newtons. Also shown on here, this gray range are sort of the range of cohesive forces between particles of this size, between millimeter particles, micron particles, meter-sized particles. And what you see for this milligee environment, the cohesion forces and the weight of these bodies are approximately equal when you get down to millimeter-sized grains. Now, for the cohesion effects to really be pronounced, you usually want those to be 10 times larger than the weight of an object. But that's just dropping down, 1 or 2 of these ticks, maybe into the 100 micron size grain size. So what this tells you is that you don't expect a pile of sand to act like a pile of sand on Phobos because the weight of those sand particles is a lot less. And the fact that they have some cohesive forces between each other starts to become more and more important. This is a very interesting thing that we have been studying, and in fact, we believe strengthens some rubble pile asteroids. This is a slightly different version of the same thing. Here, we're actually dividing the weight of a particle, or the force on a particle by its weight. And again, we can look at sort of the milli-g range of accelerations that we expect to find on Phobos and Deimos. And this really tells us the same thing. Particle sizes of around 1 millimeter. The weight is equal to the cohesion between these guys. So we do expect there to be some differences for how the regolith behaves and flows and the like. As I just said, at Phobos and Deimos, is straight scaling of cohesion versus weight predicts that millimeter-sized grains have similar properties to a cohesive powder on Earth. And the one cohesive powder that we're all familiar with is flour, because that behaves very differently than sugar. Sugar has larger granules, they weigh more, and because of that, the cohesive forces don't have as much effect. Flour is a lot finer, down to the 10-100 micron size scale, and it flows and behaves much differently. Probably more significant for Phobos and Deimos is that these weak cohesive forces in the fine-grained regolith provide an overall level of strength that could be important for geophysical processes. In particular, the regolith blanket on Phobos may be relatively packed due to tidal stresses and ejecta re-impact, and that could allow it to achieve strengths found at depth in lunar regolith. So it might actually behave more like lunar regolith in terms of its cohesive properties. And also, it's something that we might expect is that the cycle of impact regolith recirculating around Mars and hitting again on Phobos and Deimos may actually lead to a very fine regolith grain size, or very a size distribution that goes to even finer sizes, maybe again like we find at the moon, and that actually leads to greater strength in the regolith and can strengthen the overall asteroid. I do note that you had I don't know if you had a talk on this, but one of the papers that was referenced from a few weeks ago actually has some interesting discussion about the tidal stresses acting across Phobos, and they're implying some strengths and the like from that. So those are a couple comments just on scaling non-gravitational forces into this environment. I think it's a topic for a lot of potential study. It's not one that I've looked in particular at for this particular environment, but would definitely be of interest in the future. So I'm going to come back to the geopotential again and talk a little bit more about what it tells us and what sort of constraints it gives us in terms of moving across the surface of a body like Phobos or Deimos. So first of all, here's the geopotential again. This is a copy of that previous equation. Interesting thing is if we add kinetic energy relative to the Phobos system to this guy, is this 1/2 v squared. That's actually a constant. It's a constant of motion. It's just like the energy, except being the energy relative to an inertial frame. It's the energy relative to this rotating frame in this Mars tidal gravity field, and that has some interesting implications. So let's say we have an astronaut standing on the surface of Phobos, and he takes a ball. He's standing at a position r0. He throws the ball with a certain velocity v0, and it flies through the air or about Phobos, and it lands somewhere else on the surface. Well, during this whole transit, we actually have energy conservation. So we know that 1/2 v0 squared plus the geopotential at that point has to equal 1/2, the impact speed squared plus the geopotential at that point. And in fact, if you take the difference of these velocities and we form this guy, we know that this quantity has to be positive for the ball to be able to reach this R1 point. more generally, if we just assign an energy to a particular particle, you can actually map out surfaces on or regions on the surface where this particle could go or where it may not be able to go. And this really allows us to talk about the geopotential in a slightly different way, which for these small bodies actually makes more sense than an altitude or a geophysical altitude. And that's in terms of speeds that it can achieve going from one point of the surface to another point of the surface. So here we really just have a remapping of the geopotential, but in a slightly different framework now. And this is what I'm called surface speed. And this is if we start at the highest point in the geopotential, standing up here on this trailing edge, and if we have like a little marble or a ball that we can roll over the surface and somehow, without friction, it rolls, in all these different ways, this maps out the speed that that particle will have when it gets to a certain point on the surface. Now I think I'll jump over to MATLAB again and show this guy. So this is the surface speed mapped over Phobos. And this gives you a feeling for how much kinetic energy you can gain as you roll or hop, or if you throw a ball from one point to another point. So here we see if to get the maximum gain, you'd want to take your ball and standing at the highest point of the potential, roll it downhill, and have it get all the way to the end of the asteroid pointing at Mars. And then we see that it would have a little bit over 5 meters per second in terms of its speed. Conversely, if you're standing at this Mars subpoint, you'd have to throw the ball with 5 meters per second if you wanted to get it all the way up to the top of the hill. So this is a really equivalent way of looking at the geopotential over the surface. And sometimes it's, in some ways, it's actually much more tangible and useful than talking about relative altitudes and the like. Because it really is talking about something that we care about, which is potential kinetic energy and kinetic energy gain, especially if we're moving over the surface. So that's the surface speed. We can compute a couple of other things too that are of interest. Surface slopes. And here what we're really doing is we have the gravity field is normal to the constant of the geopotential, and where that intersects the surface, we also have a surface orientation or normal. And if we look at the complement of the angle between these vectors, this theta, that it turns out is what we call the slope. And it's the same on, sort of the same definition on Earth, where if the steeper the slope, the tighter you have to hold on to, or the greater coefficient of friction before you start to slide. For a regolith covered body such as Phobos and Dymos, the local slope on the surface also tells us something about how strong this material is, maybe how recently it was formed. And again, this is a good point to look at this in 3D on Phobos. And here we have the slope map, or the slope mapped over the surface. And we see I think the average slope is like 13 degrees. So most of the surface is actually quite relaxed at a relatively low value of slope. The angle of repose is usually of a granular material, cohesionless. It's around 35 degrees. And we see most of the surface is well below 35 degrees. There are little regions, mostly inside of craters or on upwelled crater rims, where we get slopes that are upwards of 40 degrees, going over 45 degrees in the vicinity of Stickney. So this is another interesting feature of the body, and it sort of tells you what the local terrain will be like as you move around the body, how much work you'll have to do against gravity to go to a higher terrain or a lower terrain and the like. So surface slope is something of interest. So one thing that got me thinking, looking at some of the other talks and thinking through how material is distributed and what the geopotential is on Phobos is what the fate of ejecta are from Phobos. And I know that there was a previous talk that went through this in detail. It was quite interesting. Now what we know is that impact ejecta from Phobos immediately enter orbit around Mars if they don't escape, and that affects how they evolve. Ejecta from the backside of Phobos will preferentially go to lower radii, and there they're subject to drag, perturbations, even impact on Mars, and have apoapsis again in the vicinity of Phobos, and will most probably impact on the leading edge. Ejecta on the front side preferentially rise to higher radii. Periapsis sticks around the vicinity of Phobos or lower, and that means that they will, when they come back to Phobos or come back to that radius, they will tend to impact Phobos on the trailing edge. And you could really, when you look at the geopotential and think about it, this I think could be taken as evidence that the geopotential actually, with its high along the leading and trailing edge, probably has accumulated impact ejecta preferentially at these locations. This is because generically, one would expect the poles of Phobos to be of the highest geopotential. However, if you're layering material back onto the surface, either from a large impact such as Stickney, or even smaller impacts that are happening all the time, they will, in general, accrete back onto Phobos on the trailing and leading edge. And this has one interesting implication, in fact, that the leading and trailing edge may actually contain subsurface material that was excavated from Phobos by impacts. It also turns out, and I only mentioned this at the very end, that this leading and trailing edge are probably the easiest places to come down to the surface if you wanted to grab a sample, such as a touch and go sort of an approach that's being used for OSIRIS-REx. Here I show this again, and while we would expect the polar region to be the low or the highest point in the geopotential, and in fact it is relatively high, especially on the trailing edge, we get this very nice rounded distribution of mass, and with the apex of it actually being the highest point in the geopotential. And the slopes are all pretty uniformly low around here, although there are a number of impact craters which probably are likely secondary impacts or potentially secondary impacts. So that's sort of an interesting observation that just fell out when I was going through this. There are some other interesting things that we can also do, and it gets to geophysical properties, but also into exploration issues at a planetary moon such as Phobos and Dymos. And that's that this unique environment places restrictions on motion over the surface. And we can really think of these as speed limits for doing various things around Phobos and Dymos once you're on the surface. One speed is how fast can you go before you actually lose contact with the surface, that you actually sort of go into orbit, to go into a little ballistic trajectory where you may have a few seconds, or if you're going fast enough, minutes or longer before you come back to the surface again. There are also limits if you want to ensure that you escape immediately. Then this would be a lower limit. If you jumped off faster than this, you might escape and go into orbit around Mars. There's also speed limits that ensure that no matter how you fall or how you tumble, if you're going less than the speed, you can't escape from Phobos or Dymos. For an astronaut, that might be a very interesting number to know, because you certainly wouldn't want to fall off of one of these planetary moons and have to be picked up some long time later when you get back to Phobos again. So this is the sort of stuff that could be factored into the design of mobile devices, if you will, on the surface of Phobos. And you can associate risks with different types of motion or modes of motion, and you can trade your mobility against different risks that you're willing to take. So the first one to show briefly is the surface escape speeds. And this is if you were standing on the surface of Phobos and you wanted to escape, and if you jumped normal to the surface, this is roughly how fast you would need to jump if you actually, and this would pretty much guarantee that you would go away from Phobos locally in a hyperbolic orbit, although of course you would enter immediately into orbit around Mars. And here we see it ranges from about 9 meters per second up to almost 14 meters per second. A more interesting one, and this is something I've been doing with a PhD student, Stefan van Waal, is how fast can you walk on the surface of a body like this before you actually go into orbit. And in fact, this is a very simple calculation. If you consider an astronaut standing on a spherical, non-spinning asteroid, you can calculate that if that astronaut runs at local circular speed, they'll actually sort of levitate off the surface and actually go into orbit. And this might be a cool thing to do, but it may not be a overall safe thing to do, because you are, literally in orbit around the body. You have to wait a full orbit period before you come back down and maybe grab on again. For an irregular body like this, we can also do a similar computation. And here, it really is a balancing of your speed along the surface, the local topography, which is really the center of curvature or radius of curvature of the surface, and the local gravity field acting on you. And you can come up with a condition for what we call liftoff on the surface. And here Stefan has actually mapped this over the surface. These red regions are actually concave regions. So if you're actually running through a concave region, you can actually run quite fast. You can definitely go over 20. We just put this in here as a place to peg the values. Most of the surface, though, that's convex, you see the speeds are on the order of a few meters per second. These lighter regions, you can run up to 6, 7, 8 meters per second, and that's probably because locally the surface is more flat. Where the surface is more curved, especially around the rim of Stickney, you see that you can, it's really easy to just walking around Stickney, just go off into orbit. Where you land, you don't quite know, and you can map that out, but that's one of the concerns. And again, it's interesting to note the order of magnitude of these speeds for when liftoff occurs. And you see 4 meters per second is a pretty reliable speed limit on the surface. So there's one other sort of concept or limit for whether or not you escape from the region of Phobos. And this is what we call the surface return speed. And it turns out if you travel faster than this speed on Phobos, on the Phobos surface, that you energetically can actually escape from the body. Doesn't mean that you will, but it means that you can. And we'll look into that a little bit more with a couple slides in a second. But I want to go back to MATLAB for a second. And let's take a look at these return speeds. And what you note is there's a lot of the surface that actually has 0 return. What that means is if you're standing up in this region right up here, and if you slip and fall or you jump off the surface, you have enough energy to actually escape from Phobos and go into orbit around Mars. Doesn't mean that you will, but it means that if you take a bad tumble or somehow roll down the hill, then in fact you might achieve enough speed so that you just get swept up off the surface of Phobos and are in orbit around Mars, which would not be a good thing for your rover, your robot, or an astronaut. And we can actually, so we look at these 0 or these return speeds across the surface of Phobos, that actually if you want to go from one side of Phobos to another side, you have to go through this region where you have to be extremely careful, because if you slip and fall, you might actually escape from Phobos in general. I guess the optimal way would be sort of walk down around the southern pole. You can sort of hop over here. The speeds that we have plotted here, these are all meters per second. What this tells you is if you go faster than, say, 4 meters per second in this yellow regime, you again have enough energy to leave Phobos. Doesn't mean you will, but you have enough energy. These other regions, you see that even moving at 1 meter per second or 2 meters per second gives you enough energy to actually escape from the Phobos system. So I should explain how this works in a couple slides, and so I'll do that now. what's really going on is if you, there are a couple of special orbits around Phobos and Deimos. These are called equilibrium points. And if you place a satellite there, it's sort of like a geosynchronous satellite at Earth. It will always be in the same spot over the surface of the Earth. It orbits at the same rate that the Earth turns beneath it. At Phobos and Deimos, it's a little more complicated because of the attraction of Mars and all this other stuff, but these points still exist. And it turns out that if you have an energy less than this equilibrium point, and this is just defined by where the geopotential is identical, the gradient of it is identically zero. If you have an energy less than this point, there's actually a region around the body that's trapped to the body and can't escape no matter what you do. So that speed is the kinetic energy you need to add to the geopotential for this little surface to open up and allowing you to actually escape from the body if you jump in the wrong direction. And this is right, what we have down here is essentially how we define this, this return speed, guaranteed return speed that I plotted on the other slide. Here I'm showing this again. This is the same the same guaranteed return speed, same scale here. These two stars are the equilibrium points, and I've chosen the energy level so that this energy level of this equilibrium point are these four constant lines of the geopotential. And you see right where it intersects Phobos is where you go from a positive trapped region with some non-zero velocity to a region where actually if you have any speed at all, you might actually fall off and escape from the system. And in fact, a good example is this little point on the bottom, right on the rim of Stickney. If you are an astronaut and you're standing there, you have enough energy that defines this contour, which you see is open over here and open on the top. And trip and fall, and if you somehow bounce, you could actually bounce through this region, and then you would go off into orbit around Mars. So it's something you have to be very careful about. And it's interesting to note that even though this, energetically you can escape from this point or these other points, actually the speed you need to walk in order to levitate off the surface is in general larger than zero. So what that really means is if you're running or walking across the surface in this middle ring, and you go fast enough so that you levitate, you have liftoff from the surface, you might actually eventually, unless you can grab back onto the surface again, escape from the body. So that's a very interesting design parameter that you would have to think about and incorporate if you're thinking about doing exploration activities on the surface. Now, one more topic of interest, and I think we're doing fine on time, is the whole question of orbiting around Phobos and Deimos. Now, the orbital environment around these bodies is a great example of what we call a strongly perturbed system. And it's sort of uniquely distinct from asteroid orbiters or planetary orbiters. And in a more technical sense, it's a mixture of the restricted three-body problem and the asteroid orbiter problem. Restricted three-body problem because of the presence of Mars. Asteroid orbiter problem because of the irregular shape mass distribution of these bodies. And there are some generic things that we know and that I've computed previously, and I'll sort of indicate these in the following. So while all my surface calculations were focused on Phobos, all my orbital calculations are focused on Dymos. And that's just because I happened to do a study of Dymos years ago, and I'm just using those results again because nothing's really changed as far as what we know about the body. In terms of the goals about looking at orbits around these bodies, the real goal is to find stable orbit conditions, because then these are important for long duration missions to these bodies, and they reduce the need for frequent or constant control maneuvers to maintaining some sort of a presence in the vicinity of these planetary moons. Also, they're interesting to study in terms of natural impact ejecta that comes off and you can analyze whether or not some impact ejecta or some ejecta gets trapped in the stable orbits over some time period or not. So we're looking at orbits around Dymos. It's less extreme than Phobos, but still a challenge. The main parameters, the spin period's about 30.3 hours. I note that there's a typo in the chapter that was distributed. Mean radius is smaller than Phobos, about 6 kilometers. And there are several types of orbits that we can find. And what we're really concerned about is, in a very general sense, we could call the navigability. And we can say an orbit is navigable, or you could fly this orbit, if it's feasible to control the orbit with the ground in the loop. Now, anyone, if you have a joystick and you're standing there and you're on the satellite, you can, if you have some calculations and good measurements, you can probably figure out how to stabilize your motion. But the real challenge is doing this through, an hour or so time delay through the ground and making sure that you can react appropriately to errors in your navigation model, errors in maneuvers, errors in controls, and the like. So I'm using this as a very generic definition for navigable. And you can really take that to mean some of these are orbits that you would be willing to fly, multi-million-dollar satellite in, and some of them you probably wouldn't be willing to fly such a satellite in. So first are these two equilibrium points that I pointed out before, but these are both unstable and really not navigable at all. They're highly unstable with a very short time period of or time constant on that instability. So you'd spend your whole time trying to burn back to get to that equilibrium point again, because all your errors would always make you slide away from it. So those really aren't practical orbits, although they're very important for understanding the dynamical structure around the body. The other one that we've looked at are close periodic orbits, or close orbits to the system. There's really 3 classes that we can talk about. Direct orbits, these are orbits that orbit in the same sense that Dymos rotates, in the same sense that Dymos or Phobos orbit. These in general are very unstable, mostly due to the shapes of these bodies and the effect that the shape has on the orbital motion. And so these are really not that useful for exploration activities. Another example are polar orbits. These would be orbits that would go, over the pole of the body. These would be ideal from a mapping perspective. However, these also turn out to be highly unstable. And in fact, for planetary satellites in general, like Europa, Phobos, Dymos, even the Moon, although the Moon is not as extreme, these polar orbits are actually quite unstable, very difficult to fly in, and that happens to the extreme at Phobos and Dymos. Finally, we have what we call retrograde orbits. And these are orbits that go in the opposite sense of the orbit and the rotation of Phobos and Dymos. These turn out to be very stable, very practical, and in fact, you should be able to navigate them almost all the way down to the surface. And I'll show a couple examples of those in a second. So first, let's look at the Dymos Geopotential. One thing you can note that's different here from Phobos, this is the equivalent picture. And you see that these 2 equilibrium points, the energies of them intersect the surface. Dymos, that's not the case. The energies of these points all miss the surface. What that really means is if you're on the surface of Dymos, you don't have this same worry about falling off of Dymos and going off into orbit around Mars. I haven't calculated the speeds here. I could do that. It would be very simple. I've done that. I don't remember what they are. But you could probably move at several meters per second or more and not be worried at all about falling off of Dymos. And this is all driven by the fact that it's much farther from Mars, the tidal effect is weaker, the rotation rate is smaller, etc., etc. So these are the 2 equilibrium points, and you can't really use them for orbits from a practical point of view because they're highly unstable. Here's a couple of examples of 2 polar orbits started in very similar, exactly the same conditions, except one is 90 degrees rotated from the other, and here you're looking down on Dymos. You see these orbits as they rise up and start to go into orbit around Dymos, and you see that they're highly unstable. In less than a day, one of these guys impacts. In less than 2 days, the other guy actually escapes, goes off into orbit around Mars. And in fact, for orbits with inclinations between 45 degrees and 135 degrees at these planetary satellites, orbits are very, very unstable. It'd be very difficult to actually use them in a practical sense. There are other techniques you could use to fly over the poles, and I don't talk about them here, but that's sort of a very different topic. Just to show you how that that 135 degree inclination point is actually important, I've got just two orbits shown here, and I'm plotting the eccentricity as a function of time and the inclination as a function of time. And they're both started off in almost the exact same initial condition, a little bit different. One of them is tuned so that their inclination initially goes down, and they go into this zone between 45 and 135. And you see what happens is within 2 days, this guy impacts. The other guy is tuned so that the orbit initially goes to a slightly higher inclination. And actually, this guy stays stable over a long time period. Ultimately, I'm not sure what he does, but this is 10 days. So this orbit in and of itself should be navigable, although you'd be worried that if you have a small error, you get into this other orbit, you might hit the surface. This just reiterates the fact that orbits with inclinations above 135 degrees are the best bet for stability. Now here are some other orbits around Dymos. These are the direct orbits I talked about. So if Dymos is rotating in this sense, if you see the cursor of my arrow, these orbits are orbiting Dymos in that same sense. And it turns out these are all pretty unstable orbits, even though they look somewhat attractive for getting close to the surface of Dymos. But I wanted to show you those. What are perhaps the most practical orbits to consider around Dymos and Phobos are what we call retrograde orbits. So here, let's look at the bottom one. This is looking down the pole of Dymos. So again, if Dymos is rotating in this counterclockwise sense, these orbits are actually going around Dymos in a clockwise sense. So they are what we call retrograde. And for Dymos, these are all actual periodic orbits, which means that they repeat themselves every orbit period and follow the same terrain again and again and again. Remarkably, these are all actually stable at Dymos. And you see when you get very, very close to Dymos, actually the mass distribution of Dymos is acting on this orbit, and this figure on the right really shows it, actually rotates it out of the equatorial plane and sort of aligns it with the mass distribution as you get smaller and smaller and smaller about it. Here, if you look down, you see you're actually flying over part of this orbit. Now, these orbits are also nice because they extend to farther and farther and farther away from Dymos. And this is sort of a zoomed out view of some of these orbits. These close ones were the ones we were just looking at. And so these are all going retrograde, so they're going clockwise in this plot. And they're all very stable. And when you get far enough away, they actually look like relative orbits that we see in Earth orbit. So any astronauts looking at this would recognize this 2-to-1 ellipse immediately. And what happens if you get far enough away from Dymos, the gravity field of Dymos doesn't matter anymore. And in fact, we have this Closey-Wilshire equation type of motion. As we get closer and closer to Dymos, the mass distribution of Dymos matters more and more, and at some point almost dominates over the sort of motion. And that's what you see here in this previous plot, these very close orbits around Dymos. Although I do note that these are all stable and would be good candidates for doing observations of these moons. A couple of final plots. An important consideration is knowing how fast you're going relative to that satellite surface. And at Dymos, this is a plot of the orbit speed relative to Dymos as a function of your distance in the x direction. Go back to here. This is 100 kilometers distance x direction from Dymos. On this plot, it's over here, and when it goes through that 100 kilometers, it's going at about 11.5 meters per second. As you get closer and closer to Dymos' surface, the magnitude of the speed actually decreases. And those very close orbits are only going over the surface at 4 or 5 meters per second, which is not very fast. If you drop something from, I don't know, 5, 10 centimeters, that's going at 4 or 5 meters per second when it hits. So that's something you could design a device to withstand that level of impact onto the surface. This is a close-up view of these speeds at these closer distances, and you see they actually just hang out around 4.5 meters per second. The similar relative speeds at Phobos are on the order of 10 meters per second or so. It's a bigger body, so the impact speeds, if you drop something ballistically from the surface, are going to be a little bit larger. But again, this is it's an important design consideration, and it tells you what sort of energy you would have to dissipate if you actually wanted to eject something from or down to the surface of one of these bodies. Okay, so I think my hour is about up, and a couple of conclusions. I believe that the study of the geopotential of Phobos and Dymos provide us a lot of insight into these bodies. And in fact, when you look at the highs of the geopotential and how they're distributed, it's actually consistent with impact ejecta sort of falling back onto Phobos, almost blanketing it along the trailing edges. And that, I believe, has implications for sampling the interior of Phobos, since the stuff that comes back is actually exhumed from the subsurface from the impact. Also, the dynamical environment about these bodies is unique and highly complex. Despite this, it's always possible to design your surface and close proximity motion around these bodies. You just need to understand what the environment is like and take that into consideration. Ballistic deployments, you should be able to withstand several meters per second of impact speed. You can actually use hovering approaches. I haven't really talked about this here, but they're sort of interesting, and they're in fact easiest along that leading and trailing edge, where you might have this accumulation of ejecta back onto the bodies, especially for Phobos. And so that could have some interesting applications for surface sampling of these bodies if you didn't want to actually land on the surface. And finally, surface motion is possible, but has some very unique constraints if one wants to ensure that you stay on the body surface and don't escape into orbit around Mars. And in fact, you can show that going from one end of Phobos to the other always has the risk of escape, because there are always these regions where even with without moving, you're already at a high enough value of the geopotential, so if you slip and fall, you might actually escape away from the body and go into orbit around Mars. So with that, I'd like to thank everyone for their attention, and I'd be happy to take any questions that people might have.
Okay, Dan, thank you very much. You're hearing digital clapping in the background right now. So, very interesting talk. I'm gonna use the moderator's prerogative and ask one of my own right now. And you were saying that Phobos is probably fairly blanketed by ejecta. What about Dymos? Because Dymos looks fairly blanketed already. Is there something dynamic about that would suggest easier or more accretion?
I don't know if it's easier or more, although you can imagine that ejecta from Phobos could very easily end up on Dymos as well. I haven't gone through the calculation, but for a big impact, you might have relatively high ejecta speeds, and that would bring stuff up to a higher altitude where Dymos could just sweep them up. Also, any impacts on Dymos, again, is going to have the same situation where a lot of that stuff could come back to Dymos again. Now, the models we have of Dymos aren't as good, but I do know, at least the model that I have, is that Dymos has this really large dimple in the southern pole. I don't know if that's a real thing or if it's just a modeling artifact.
No, it's a
But
real thing. You can see it in pictures.
yeah, so if that were a crater, an impact crater or something like that, or arose from that sort of a thing, you can imagine a lot of stuff being spewed out and coming back to the surface over some time period.
I think that the gravitational situation on Deimos makes it a better target for exploration.
Well, there's a couple things in its favor. First of all, it costs a lot less to get to the Dymos orbit because you don't need to go as deep into the Mars gravity well. Also, if you want to do things on the surface, you don't have these interesting questions about if I trip and fall, do I escape or not? Because it's again the whole surface is inside of its what we call its Roche lobe, and what that means is that you can be on the surface, you can move around, you can define a well-defined speed limit, and as long as you stay beneath that, you'll never leave this. You'll never escape and go into orbit around Mars. So those two things by themselves, from a design and optimization perspective, point towards its favor. Geophysically, I'm not sure which would be of more interest, and it really depends on what theory of formation you hold to for these objects. But yeah, just from a straight surface motion, yeah, Dymos would be safer.
Okay, do you believe that the bluer spectral unit to the west of Stickney is due to the abundance of material sampled from Phobos interior by deep excavating impacts?
That is an interesting question. I'm probably not the right person to talk to about that because I haven't actually done detailed modelings of the Stickney ejecta field. I know that there was an earlier talk that looked at the ejecta field from Stickney in great detail, and someone like that could probably give a better answer. That being said, bluer is usually affined with finer materials. Now I don't know if I know my directions on Phobos that well, but is west in the leading edge or the trailing edge?
Oh, you got me on that one.
Okay. But if it's at one of the leading and trailing edges, you might actually have ejecta that's been hit and pummeled several times, coming back to the surface again and again and being reprocessed by a new impact. That could create a finer material, which may actually have a bluer spectral tint to it.
One of the students says he believes west is leading.
Okay.
So the next question is, earlier in the class we spoke about the possibility of rolling boulders forming the grooves. However, it seems here that anything moving with a non-zero velocity is at great risk of leaving Phobos, making rolling and bouncing boulders unlikely. Is this true?
What we're giving are sort of energetic limits. However, for any particular boulder that you have rolling on the surface, we could certainly do a calculation and see, does this boulder, does it eventually, does it come off the surface? Does it go into orbit? Does it escape? From an energetic point of view, you have to be pretty careful moving across the surface. And if you're moving at more than a few meters per second, you're very likely to actually go into orbit and have periods of ballistic motion. You might come back to the surface again, but you're definitely in orbit around the body then. And depending on where you roll off the surface and what your speed is, these zero velocity surfaces might be open to you, and a couple of bad bounces, you could actually fall off and go back into orbit around Mars. So I'm
Okay.
not saying that you can't have rolling boulders on the surface, but it certainly would have to, this would have to be factored into the dynamics of these guys, because a couple meters per second is not that fast, and yet that's enough to send you off into orbit. And so you'd have to do those calculations carefully.
Related to that, in regions where a positive non-zero speed can result in Phobos escape, would a cohesionless object be stable sitting on the surface? Is anchoring necessary, theoretically, not just practically?
No, just because your energy is sufficient for you to escape, what really matters is what direction does that initial velocity vector go? And if you're a cohesionless particle and someone slides you tangent to the surface, you'll probably be okay. Because if you remember, those speed limits were 2, 3, 4 meters per second. If you're sliding over the
Okay.
surface and you're not lifting off, you should be okay, even though your energy is high enough for you to escape. If you hit a bump, though, and you go up into orbit, you'd have to really trace out the sort of the flow lines in the dynamical space to understand if you had a risk of actually leaving and going off and going somewhere else. So just because you're in this zero speed region doesn't mean that you can't move or else you'll escape, but it does mean that you should have some caution about how you move. That's why I think those regions are probably more relevant for exploration activities, because there you've got people that are hopping, or you're somehow mobilizing yourself across the surface, and you're giving yourself unnatural initial velocity vectors, and those are some of those could turn into escaping maneuvers. But just if you're a rock
Okay.
sitting on the surface, I think it's fine.
Okay. Um, Ken points out a couple of things. Keep in mind that the orbital evolution of Phobos in the past potentials would have been different for if it was farther out.
That's right. That's right, and that could actually be that's pretty easy to study. Is just one parameter that you can turn to mimic how the geopotential changes over time.
Okay, and then another comment. The preferential return of ejecta from impacts on Phobos returns generally to the opposite hemisphere from the original impact. Not necessarily just to the leading or trailing hemisphere. E.g., a north polar impact would generally return to the southern hemisphere.
Yeah, that's true. Although when you average over all possible ejecta directions, it's the leading and trailing edge will have a preference, just because that's the direction of secular motion. The other ones, you have to be there's a strong timing constraint, being at the right place in the right time. Whereas the ejecta that takes off in the same plane of the orbit is going to have a much higher probability of re-impacting along the leading and trailing edges, really just as a function of the geometry and the function of the relative motion between those ejecta particles and the motion of Phobos or Dymos.
Okay, a slightly different point. Given the gravity of Phobos, clearly anchoring would be required for exploration. Considering the rubble pile nature of the body and low cohesive forces between particles, do you think providing an adequate anchor is even possible?
Well, first of all, I'm not sure that the cohesive forces are low. They might be higher, especially if the regolith is quite fine. You could, you could tamp it down and probably use the regolith as a pretty effective anchoring substrata. I would almost think. It's not something that we've studied before, but just thinking about how everything scales, you might actually be able to, how you can sink a stake deep into the sand, and actually it gives you a pretty stable anchor if you if you design that anchor correctly. Um,
Anybody who's tried to do sediment coring in loose sediment very quickly notices how cohesive that stuff is, even when it's not well consolidated, especially when you're trying to pull out the damn core. And so it develops lots of friction really fast. Let me see here. So, next question. Does the liftoff speed indicate that you can't really walk around a large crater on Phobos?
I think it means that you have to maybe take baby steps sometimes.
Okay. So you develop kind of a Phobos shuffle, is that it?
Yeah, it's Phobos shuffle, because you don't want to go too fast, because you might go into orbit. Yeah, but it's sort of it's a very cool concept that you can actually, run off the surface or walk off the surface. If you're just walking too fast from one region to the other, you might suddenly find yourself floating around.
Okay. So do you think that the leading and trailing edges are probably the safest places for astronauts to move around? And then you just have to be more careful when you move between those two areas.
No, actually I think those are actually in the highest in the geopotential. So those would be where you should worry about slipping and falling off the body.
Okay.
On Mars, the safest places are really at the sub-Mars point, or on Phobos, the sub-Mars or the anti-sub-Mars, whatever we call that.
Okay.
On Dymos, I think the whole surface is very safe. But on Phobos, it's that especially the leading and the trailing regime, where I would be a little worried if I were sort of scaling across the surface of that. However, for a spacecraft, if you wanted to take a spacecraft and sort of rendezvous with the body, touch it, like a OSIRIS-REx type of sampling, and then move away again. Actually, the leading and the trailing points are probably dynamically, in terms of developing a control system and the like, probably very relatively attractive. And especially if they've been accumulating this impact ejecta onto themselves, that might work quite well.
Well, what if you had some sort of a habitat that you were maneuvering around Phobos? It sounds like it would be very easy to essentially hop from one area to another given the geopotential, because what you're doing essentially is hopping into a new gravity regime very easily. Mm-hmm. And then you can maneuver around and drop down into the Phobos gravity regime without much effort.
Yeah, especially if you have some of those orbits that are, pretty close to the surface. If you have a station up there, you could hop down. Right, you could sort of drop down to the surface, do some stuff, probably on your own two legs, hop back up, and catch it again. You want to be a little careful. Yeah.
Well, but if you had a little maneuvering, so essentially what you'd be doing is hopping out of one maneuvering mode and into another.
Yeah.
Because you're essentially popping off of Phobos gravity and into the sort of trans-Mars geopotential.
Right. And going into like a retrograde orbit is actually pretty stable, and you're actually not going to, the probability of escaping there, even though you have highness, the speed is relatively high, is actually quite low. But to study that gets a little more complicated and beyond sort of what we're talking about here.
Okay. Another question. If there is preferential re-accretion of material into the leading and trailing edges of these moons, would we expect this to be observable in the spectral data? Also, would the dynamical evolution of Phobos and Dymos be significantly impacted by this non-uniform accretion? Well, I think we do see it in the spectral data. But go ahead and discuss that, and also whether it affects the orbital evolution.
So first off, yeah, since you're looking at material that's been pulverized by an impact, yeah, to me it makes sense. Just not even from compositional standpoint, but just from a size distribution standpoint, that the stuff that would be swept up should have a finer grain size and maybe have a different spectral slopes or spectral characteristics. In terms of the orbital evolution, I don't think it's going to be that significant. It would first of all have to be systematic on one side or the other for it to have an effect that averages to something that would push it in or out. Um, and given the tidal, I think the tides are acting pretty rapidly on this body, so it's moving relatively fast just from the tidal interaction. I sort of have the feeling, although I certainly haven't looked at anything, I had the feeling that might swamp out any small effect from preferential ejecta accumulation. Although if there were ejecta accumulation that was preferred on one side or the other, ultimately that could add a little bit of secular rate to the body.
Okay. A note, keep in mind that very small Mars orbiting particles are quickly driven from the Martian system, mostly by solar photon pressure. The lower limit of particle size that remains in orbit around Mars from the literature is a few dozens to hundreds of microns. And so you would expect, I guess, from that that although you would be re-accreting fine material, there would be kind of a lower limit to what you accrete, in the tens to hundreds of microns range.
Yeah, it depends on how rapidly the fine stuff gets driven off. Eventually, the fine stuff gets a very eccentric orbit. That does take a little bit of time, and depending on how you bias the ejective field, you might have some fine component that still sweeps across the surface at some point in the future. So, I mean, that certainly is true. If you get small enough, then stuff might escape too fast. But I'm not sure exactly where the timing in that limit would lie. People may have looked at this now.
Yeah, I think there's been some work on that, but I'll have to look it up. How significantly does surface texture / irregularity affect cohesive forces?
I don't think that has much effect because the cohesive forces it's really a granular mechanics type of phenomena. And what it really depends on ultimately is the size distribution and the porosity of the regolith and of the material on the surface. So if you have stuff that's really fine and if you crunch it together, drive out porosity, the cohesiveness of that material the effective strength of this clod will actually go up. If you have stuff that's very loosely packed and is larger, the cohesion will be less and less important. So whether or not the surface is irregular or not doesn't have, that doesn't speak to that particularly. Although if you do have a very cohesive surface, so the regolith is very cohesive, it can sustain higher slopes. And you might expect, especially when we get to smaller and smaller size scales, that you see it more and more rugged. Whereas if it's all water or very low cohesion stuff, it would tend to spread out and be smooth everywhere. I don't
well,
know
from the
yes. No,
from
go ahead,
the plots that you showed suggested that there aren't a whole lot of slopes that are substantially below or substantially above the punitive angle of repose. So that would suggest that there's not a lot of excessive cohesion in the surface material. Comment?
Yeah, although the size scale we're looking at is still relatively large. I guess I don't know how big the facets of the model that I'm using are, but I bet you they're tens of meters across still, if not more. So at a global scale, even if it is cohesive and can sustain higher slopes over time, you still expect that to be worn down by impacts or other processes, seismic effects or whatever. It's when you get to the smaller scales that we don't have as much data on that that you have the possibility of maybe having a more irregular, more rough surface with higher slopes. And we do see
that's one of the principles.
Yeah, we also see.
Sorry, go ahead.
Yeah, sorry. We see a few regions where there are sort of large areas with slopes, up to 45 degrees. So that's, that certainly is interesting in and of itself. Sorry, go on.
The other thought I have there is that if you're winnowing out fine material from the solar wind, that maybe Phobos is somewhat depleted relative to most near-Earth asteroids in fine materials, and so it may be slightly less cohesive because it has this fine material depletion.
What do you think the depletion would occur, or why would that occur?
Well, from the solar wind, from the re-accreting stuff, the fine stuff would be swept out by the solar wind. But on the other hand, you're re-accreting a lot of stuff pretty fast, so that might not have much of an effect.
Yeah, because actually I think at an asteroid even though the fine stuff does get blown out of Mars orbit, it's actually Mars can hold a lot finer stuff around than a small asteroid. So you might actually think that a small asteroid, the solar radiation pressure might actually be much more effective in driving out finer materials that are, ejected from an impact. Whereas Mars has this circulatory system that can bring the stuff back again. So yeah, it might be the opposite then.
Okay. One last question. Although Dymos may be safer bet gravitationally, would the larger amount of debris buildup cause more of a problem for operating on the surface if the fine material appears to be thicker on Dymos than Phobos?
Yeah, I think for both bodies, the fine material is present and would have to be mitigated. So, whether you have a decimeter or a meter of fine dust, you probably are going to have a similar way of dealing with it. So my intuition is that that first of all, that's very important that you understand how to deal with the dust and the stuff which could be quite cohesive and be pretty difficult to get off of a system if it starts to adhere to it. And while Dymos might have more dust than Phobos, though I'm not sure if that's the case, there might be some other measurements that show that. I would really think that both of them would present an equal challenge.
Okay. Well, thanks very much for the talk and also the extensive question and answer session. And it's been fascinating and quite insightful, so I greatly appreciate it.
Good.
And thanks to the online audience. And you can hear more virtual applause coming in through the interwebs. Thanks a lot, Dan.
All right. Thank you, Dan.